we're going to take a look at using de Moivre's theorem and also along with binomial theorem to determine trig identities. Now what's really cool about de Moivre's theorem is the simplicity of multiplying complex numbers really quickly. And remember, using de Moivre's theorem means you need to write your complex number in polar form. So let's take a look at a first set of trig identities that you're familiar with, which are called the double angle identities. So sine 2 theta, remember, is equal to 2 sine theta cos theta, and cos of 2 theta equals cos squared theta minus sine squared theta. And yes, I know you can write those using just one ratio, but we'll just leave this identity in its primitive form. So how do we prove these trig identities? We're going to use complex numbers to do this. First up, we're going to let z equal cis 2 theta. We're going to let cis equal, so z equals cis theta. And then we're going to now find z squared. Okay, so what we're going to do is we're going to take this expression and raise it to the power of 2. So hopefully you can see here, this is application of de Moivre's theorem. What we're going to do now is we're going to raise the modulus, which happens to be 1, to the power of 2, which is also 1. And we're going to multiply the argument by 2. Alright, so it just happens to be cis 2 theta. That's it. So that's the answer. Now, this is written in polar form. We can expand this out. So we can write it as cos 2 theta plus I sine 2 theta. So what's happened here now is, using a polar form of a complex number, I have squared this out using de Moivre's theorem, and I'm just going to initialize it as DMT. Okay. Now I can do this a different way. So I can write my complex number in Cartesian form. So if I expand this out first, I can write this as cos theta plus I sine theta. Right, so this is Cartesian form. And then I'm going to now square this expression. So over here I'll do the working. So we've got z squared equals cos theta plus I sine theta and squared. Now when you look at this, to square it I'm going to have to use binomial theorem, or really I'm just squaring it out because this is just a pair of 2. It's not a difficult one to work out. So it's going to be cos squared theta, and then we move on to plus 2 lots of cos theta and I sine theta, and then finally plus I squared sine squared theta. Okay, so I'm just using the rule a plus b all squared equals a squared plus 2ab plus b squared. Okay, hopefully you remember that. And then I can simplify by writing the real parts together. So you should be able to identify this is the real, this is the real. I'll just put an r next to those. So we've got cos squared theta plus sine squared theta. Sorry, not plus, minus. Okay, because I squared equals -1. Okay. And then we've got this part here is all imaginary. Okay, so this will be plus imaginary, and then I'll just write this as separate term there. 2 cos theta sine theta. Now, hopefully you can see something interesting already before I even continue on. So this is the real part. Okay, and this is the imaginary part. When we equate the components on both sides, right? So this is the Moivre's theorem, and this is binomial theorem, which I'll just initialize as BT. You've got the real part here, and you've got the imaginary part here. Can you see it? This is pretty cool. So equating components, okay, the real part gives you cos 2 theta equals cos theta minus sine squared theta. And then the imaginary part, sine 2 theta equals 2 cos theta sine theta. There you go. So those are the double angle identities. Now, did you know there's actually other identities such as the triple angle identity and so on and so on? You can have ones for different values. Now, this is quite useful expression to have. Maybe you would have seen this in calculus, okay? Remember that it's hard to integrate functions that have squares in them, so you'll have to use one of these expressions rearranged. So, you know, as a consequence, you could also integrate functions that have cubes in it, okay? So, just mentioning quickly, the integral of cos cubed x dx can't be worked out easily, and there's no identity for it. If only there was something with cubes that I could use. And yes, there is some relationship to cos 3 theta. Alright, so I'm going to now set up a question for you to try, and we'll go through the proof really quickly. We're going to do a very similar process, okay? So we've got de Moivre's theorem and binomial theorem used in conjunction together to get the identities. Alright, can you work out the triple angle identities? Okay, so the question is, find cos 3 theta equal to something and sine 3 theta equal to something. Alright, you can pause this video and try it yourself. I'm about to go through the solution now. So to do this, we start off with de Moivre's theorem. So first up, let's let z equal cis theta. Okay, so this is the polar form. So when you do a polar form, you're going to use de Moivre's theorem. Alright, that's going to look like z cubed equals cis 3 theta. Expand that out, so z cubed equals cos 3 theta plus I sine 3 theta. Okay, done. Now on this side, we're going to expand this out, cos theta plus I sine theta. Okay, so z cubed, and this is the binomial theorem, equals cos theta plus I sine theta all cubed. This is where there's a little bit of work to do. Okay, remember binomial theorem, we're going to use the Pascal's triangle, 1, 3, 3, 1 as our coefficients. So we're going to cube this one first, so you got cos cubed theta plus 3 lots of this one squared, and then 1 lot of this I sine theta. Okay, moving on. Actually, I'm going to run out of space, so I'll write it down here. Plus 3 lots of cos theta, and then 2 lots of these, so I squared sine squared theta, and then finally we just cube that last term, so plus I cubed sine cubed theta. Okay, so we need to identify which parts are the real parts. So any even amounts of I were going to be real. So there's real part there, and this part is real also. Okay. So z cubed equals cos cubed theta, and this will be minus, because the I squared will turn into a subtract, 3 cos theta sine squared theta. Okay, imaginary parts. So plus I, this will be 3 cos squared theta sine theta, and this is I cubed, so you just take out one of the I squareds out, so it would be minus sine cubed theta. Okay, so we'll just mark that in. Okay, so this is the imaginary part, and this is the imaginary part. All right, so overall we have, this is imaginary. Okay, this part over here is imaginary, and this part here is real, this part here is real. We're going to equate the components, so we should write equating components. Hopefully you'll see, just like in the previous example, that to get the cosine you equate the real components. Alright, if you want to get the sine identity, then you equate the imaginary components. So cos 3 theta equals cos cubed theta minus 3 cos theta sine squared theta. I know it's very long, but it is pretty cool. You've got an expression for cos 3 theta. I'm going to stop here just for one moment and ask you, is it possible to write this all in terms of cos theta? So I don't want the sine squared theta here. Yes. Okay, so remember, this is the same as 1 minus cos squared theta, which is the Pythagorean identity. Okay. If you like, you can pause this video again and just have a go at changing it all in terms of cos theta. So now I'm going to go through that solution and show you what it looks like. So you're going to have cos cubed theta minus 3 cos theta in brackets 1 minus cos squared theta. So hopefully you can see there's a cos cubed theta here, and there's a minus 3 multiplied by this other cos squared theta here as well. That gives me another plus 3. So I've got a total of 4 cos cubed theta minus 3 cos theta. Okay, that's what cos 3 theta equals. Isn't that amazing? Okay, so let's quickly work out the sine 3 theta as well and get a similar identity. That over that. Okay, and I want to write it all in terms of sine, mostly because this is sine, so it would be nice to write all this in terms of sine. Okay, and then finally let's put all the cube terms together. So negative 3 sine cubed, and then minus another 1, and this is just 3 sine theta. So I've got 3 sine theta minus 4 sine cubed theta. Great. And what's amazing is it looks very similar, like there's anti-symmetry between the two. Okay. And that's how you can use de Moivre's theorem and the binomial theorem together to prove trigonometric identities.